Hi, this is a tutorial for CSE403 for Professor Keith Schubert at CSUSB. Today we're going to be looking at the initial value and final value theorem. So let's start with an example here. I have a problem written down. It's a complex frequency domain problem, so it's f of s, and we want to find what happens when t equals 0 and when t goes to infinity. Now we have a couple theorems for this that say we can find those values directly from the f of s function here, the complex frequency function, and we don't have to do an inverse Laplace back to the time domain to an f of t function in order to find these. And so we have two theorems for that, the initial value theorem and the final value theorem. So the first one, the initial value theorem, just says that we can say the limit as t approaches 0, f of t equals the limit as approaches infinity as f. So this is the initial value theorem here. And this just simply states that as our time domain dependent function f of t goes to 0, that's equal to our frequency dependent equation f of s when it goes to infinity, actually s times f of s. So what we do is we take our equation f of s, multiply it by s, and then take that to infinity, and that'll be our initial value. And similarly, when we take the limit as t approaches infinity of f of t, that equals the limit as s approaches 0. And this is the final value theorem. So this is saying that as t approaches infinity, as t reaches its final value, or f of t reaches its final value, that happens when we take the limit of s goes to 0 of s times f of s. So it's important that we multiply by s before we evaluate these limits, otherwise we won't get the correct answer. So I have this function written here. So let's go ahead and find the initial value and final value using these theorems. So first thing I'd want to do here is some quick algebra. Let's distribute the two and distribute this and combine these. We'll do that in a couple steps here. So what is that? 2s squared plus 4s plus 12 over, and let me combine those two real quick. And that's s plus 3. So again, we can combine here, distribute, and the top stays the same. And down here we get what? S cubed plus 6s squared plus 6. Okay, so we haven't really done anything. We've just made this in a little bit better form to work with. So both of our functions say we want s times f of s. So the first thing I want to do here is let's go ahead and multiply this by s. So s of s equals, and I can just go ahead and put an s here and just distribute it. So all I did was just multiply everything on top by a power of s. So now I have it in the correct form to take my limits. So let's go ahead and take those limits here. I can just kind of shift this over. So the first thing we're going to do is the initial value. So the limit as s approaches infinity of 2s cubed plus 4s squared plus 12s all over s cubed plus 6s squared plus 11s plus 6. So we want to evaluate this as s goes to infinity. So if we look at this, if we just look to put infinity in here, this blows up on us. You know, infinity plus infinity, you know, it gets to the form infinity over infinity. That's an indeterminate form, and because it's infinity over infinity, indeterminate, quickest thing for me to do is L'Hopital's rule. So we'll just take the derivative of the top and the bottom. So the limit as s approaches infinity of 6s squared plus 8s plus 12 goes 3s squared plus 12s plus 11. So okay, got the derivative of the top and the bottom. So let's go ahead and plug s goes to infinity. Let's take the limit. So this infinity again blows up to infinity over infinity. So L'Hopital's rule again. Take the derivative of the top and the bottom. 12s plus 8 equals 6s plus 12. Again, plug in infinity, or however you want to evaluate infinity. We get again infinity over infinity. So L'Hopital's rule one final time, and we get 12 over 6. And the limit as s goes infinity of 12 over 6 just equals 2. So there, and the final value theorem, or the initial value theorem, sorry, states that f of t, or f of 0, should equal 2, because that equals the limit as s approaches infinity of our original function. So that's the initial value theorem right there, and that's our initial value. So let's go ahead and look at the final value now. Just go ahead and get another piece of paper here. And so let's just write this up here. The limit as s approaches 0 of our function. And our function is 2s cubed plus 12s over s cubed plus 6s squared plus 11s plus 6. This limit's much easier to evaluate. If we plug 0 in, the top basically just goes away, right? 0 to 0 to 0. These all go away. We're left with 6, so at least we don't end dividing by 0. So that just equals 0. So that, as s goes to 0, remember that gives us our final value. So f of infinity, as it were, goes to 0. So our initial value, as we found earlier, was 2, and our final value should be 0. And that's basically the initial and final value theorem. If you already have the equation in the complex frequency domain, it makes it real easy. Just multiply by s, take the appropriate limit, and use your rules of limits, and you should be able to get the answer pretty painlessly. So that was the initial and final value theorem. Thanks.